welcome back. This is Unit 3.2 on periodic trends. In your textbook, it's page 184 to 202. And in your study guide, it's going to be 74 through 79. All right, so periodic trends. We need to know trends on the periodic table. There's 3 trends that we need to know. But before we do that, we're going to review real quick about electrons and how electrons fill up the rings. So we're going to be doing that by looking up Bohr models. All right, so you remember the scientist Niels Bohr. He is the scientist who came up with this planetary model to show electrons around the nucleus. And these Bohr models we use still today, even though we know this is not really what happens, so that we can illustrate and talk about other things about the atom, like periodic trends. All right, so Bohr model. Okay, so make sure we have this Bohr model from Niels Bohr, and it's also called the planetary model. All right, so for this first atom, let's talk about helium. All right, so helium only has 2 electrons, and then so these 2 electrons are going to be on this first energy level. Okay, so the first energy level can only hold 2 electrons. All right, and so helium just has 1, hydrogen just has 1, and then helium is going to have 2. So after we get those 2 electrons on this energy level, we're going to have to move up to another energy level. So once we add this second energy level, every energy level after this can hold 8 electrons. So that's a very important number in chemistry as far as electrons on orbitals are concerned, 8. So if we look at lithium, lithium has 3 electrons. So it has the 2 on this first shell, and that's the 1s shell. And then it can hold 8 on this one. So 3 electrons total is going to be lithium. We were to add another electron here for a total of 4, that's going to be beryllium. And then on over, it's going to keep going up by 1 until you get to neon. Neon has 10 electrons, so it's going to have 8 on this outer shell and 2 on the first shell. So once it gets 8 on this shell for neon, then we have to add another shell. So once we add this shell, then we have the 2 on the inside, 8 on the second shell, and then now we're down to the third energy level, or the third orbital. So we start all over again. So sodium is going to have 11, magnesium is going to have 12, aluminum is going to have 13, silicon is going to have 14, phosphorus is going to have 15, sulfur is going to have 16, chlorine is going to have 17, and then we're back to a noble gas again, argon. Argon is going to have 18. So when it has 8 electrons on that shell, then we're going to go down to another energy level and add another shell. All right, here's where it gets a little bit tricky. So now we're going to get into the 4th period, which includes the 3D suborbital, and this is for the transition metals. Now, I've told you all year long that transition metals do weird things. So you can think about it like this. So potassium is going to add its first electron here, and then calcium is going to add an electron on this shell. Then you're going to get to the transition metals, which starts with scandium and titanium and vanadium. Well, the way I like to think about those is those electrons don't sit directly on that orbital. What they do is they fall down to this suborbital. So you're going to have these 10 electrons, 6, 7, 8, 9, 10. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that's 10. So by the time you get this electron here for zinc added on, Then we go back to the p orbital for gallium, and it starts adding electrons back on this outer shell. So these are the valence electrons. So if you keep adding all the way over to krypton, you're going to have 8 electrons that are on this outer shell. So that would be krypton. All right, so as we go across the periodic table and down, you can see that we keep adding these orbitals. Once you get to 8 electrons on an orbital, then it adds another orbital. So let's go back and let's look. The first periodic trend that we're going to talk about is atomic radius. So radius means the distance from the nucleus to the outside shell. So we can see here for hydrogen and helium that radius is going to be small. But as you keep adding these electron orbitals and they keep filling up to 8, you can see that the radius is now starting to get larger and larger. Okay? So as you go down the periodic table, it gets larger and larger, the radius does. Okay, so periodic trends are best understood by knowing the interaction of the protons with the electrons. And where are the protons? Okay, they're in the nucleus. Okay, so it's the interaction of the nucleus, or the protons that are in the nucleus, with the electrons on the outer shell. All right, so let's do a little bit of review here. Pardon me. What is the charge of the protons? Well, of course, the protons are positive. What is the charge of the electrons? And the electrons are negative. So if we look at the interaction between the protons and the electrons, positives do what happens between positive charges and negative charges? Well, what I'm going for here is they attract. Positive charges attract negative charges. So the positive protons that are in the nucleus are constantly attracting the negative electrons. That's why they don't fly off and zoom off into space, because if you think about, the Earth, and then the satellites that orbit the Earth they have to be traveling at a certain speed to stay in orbit. If they don't travel at a certain speed, then Earth's gravity pulls them down like this, right? And then if they go too fast, this orbit is starting to get bigger and bigger, and eventually they'll just zoom off into deep space. So it's the attraction of the electrons and the attraction of the protons to the electrons and the speed that the electrons are orbiting the nucleus that keep the electrons in orbit around the nucleus. All right, so the last question is here. Do the protons ever change in an element? And the answer to that is no. Protons never change from the same element. Like, for example, phosphorus has 15 protons. Phosphorus will always have 15 protons. It will never change. If we change the number of protons and say we add a proton to that, it's not phosphorus anymore. It becomes silicon or sulfur. I'm sorry, if we add, it becomes sulfur. We take away a proton, it becomes silicon. So protons do not change from element to element. All right. So with the attraction of the protons and the electrons in mind, we're going to look at what happens when we go across a period on the periodic table. All right, so if we're looking at sodium, so sodium has 3 orbitals, and you can see here 3 orbitals for sodium. And in that outer orbital, sodium is in that first position. It's in group 1. So what that means is these orbitals have been filled. So there's 2 here, and there's 8 here. And we've added that 3rd orbital. And since it sits in that first position, group 1, that means there's only 1 electron in this orbital here. So the protons that are in the nucleus here are acting on these outer shell electrons and pulling it in. And since there's only one electron out there on that shell, it really doesn't have, think about those electrons in that outer shell as being handles. It really doesn't have, the protons in the nucleus really don't have but one handle to grab and pull that shell in. But as we go across the periodic table, like magnesium, now there are two electrons out there. So these protons can grab onto those two and pull, so it can pull with a little bit more strength, which makes this ring a little bit closer to the nucleus. So as you're adding electrons, then there's more for those protons to pull in. So by the time on that third energy level we get over to argon and we add these electrons for argon, there should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these protons have a lot more to reach out and grab all of these handles now. So it pulls that shell in even closer. So as you go across the periodic table from group 1 to group 18, this gets pulled in more and more. So the radius is smaller and smaller. Okay, now we've already talked about as we go down a group, you're adding more and more orbitals. So of course it's like a gobstopper. Once you add more and more layers, the radius gets bigger and bigger. So if we're going to look at atomic radius as being a trend, then the largest, of course, is going to be down here. You can see here cesium is the largest, and the very smallest is going to be up here. Helium is the very smallest. All right, so if you can't remember anything else, then what you're going to have to remember this trend for radius is large left, big bottom. So as you go to the left of the periodic table, they're getting larger and larger. So as you go down, they're getting larger. So large left, big bottom. Okay, so you can see here, as you go across the periodic table, it gets larger and larger on that row. And as you go down, they get bigger. So large left, big bottom for atomic radius. All right, so the other two trends that we have to know are ionization energy and electronegativity. So write down these definitions. All right, so ionization energy is the energy required to remove electrons from an atom. So if you remember what an ion is when an atom has gained or lost electrons. So ionization energy is the energy required to remove an electron. So if we think about this, and logically, if we look, all atoms want to have 8 electrons. So as you're going across the periodic table, you're adding electrons. So as you get closer to these noble gases, the atom becomes more and more stable, and that's where they want to be. So like you can see here, lithium, beryllium, if you're looking at these as this graph, where as this bar gets higher and higher, that's more energy. As we're moving across the periodic table, you see those bars getting taller and taller. That's because you're adding electrons and it's getting closer and closer to having 8. And as you get closer and closer to being stable or to be a perfect atom, it's going to get harder and harder to remove that electron. They're going to be more stingy with those electrons and letting them go. So ionization energy increases as you go across to the right on the periodic table. All right, and then if we think about how easy or hard it is to remove an electron, let's go back to this. As you add these orbitals and these electrons get further and further away from the nucleus that's holding on to those electrons, as you get farther away, it's easier to go in here and pluck off that electron. So the closer the electrons are to the nucleus, the harder it is. So ionization energy increases as you go up the periodic table where they're getting smaller and smaller. These electrons here are closer to the nucleus. All right, and electronegativity is the ability of an atom to attract electrons. So again, as you get closer and closer to the noble gas, they attract electrons more and more because they're getting closer and closer to having those 8 electrons. All right, so if you can't remember why, then you just need to remember that for electronegativity and for ionization energy, the trend is where these arrows are showing. It's the same for both of those. So electronegativity and ionization energy increase as you go up the periodic table, and it increases as you go towards the right. Okay, and one graph that you're going to see over and over is this one. And this just shows it's the graph for ionization energy. So on the y-axis here is the energy required to remove an electron. So you can see as this noble gas right here, as the atom gets closer and closer to being a noble gas, it requires more and more energy. So helium, since it's the smallest atom on the periodic table, requires the most energy. Look, it's way up here, requires the most energy to remove an electron. But as you start a new period, lithium right here is the first element on the second period, the energy goes way, way down. Because if we were to remove that third electron from lithium, so it only had 2 electrons, it would look like helium, which is very stable. So as you add electrons like this, it gets harder and harder to remove those electrons until you get to neon, which is, again, a noble gas. Then it's really, really high energy. Okay, so these down here, these elements at the bottom, are all the group 1 elements, the alkali metals, that just have that 1 electron in that outer shell, which is the lowest energy. It's pretty easy to take that electron off. But as you add electrons and you get closer and closer to the noble gases, it gets harder and harder to remove those electrons. So you can see it goes up and back down, and then up, down, up, and down, up, down, and back up. Okay? All right, so that concludes this one. It was a very short video. Make sure you slap that like button right across the face, subscribe, and hit that bell so you'll be notified when I put up more videos.